Sample question 3.1.2, how do group and period differ? Clearly we're talking about the periodic table here, and when we're talking about a group on the periodic table, that's a column that's going up and down. And all of the things within a group are going to have the same number of valence electrons. As we're looking at periods, that's when we go from left to right across the periodic table. And when we're dealing with that, we have the same energy level. The next question, sample question 3.2.2, it says to diagram each of the trends listed in the standard 3.2.2, which says to describe and explain the trends of atomic radii, ionic radii, first ionization energies, electronegativities, and melting points for the alkali metals and the halogens. Well, for the ionization energy, we'll do IE for that. For the ionization energy, for both the alkali metals and the halogens, we increase as we go from bottom to top. The electronegativity is the exact same trend as the ionization energy. So ionization energy, the amount of energy required to remove an electron. Electronegativity, the amount of pull in a bond that one electron or one atom has compared to the other one. So as we go up, that increases as well. The atomic radius is the exact opposite for both the alkali metals as well as the halogens. From the ionization energy and the electronegativity, it actually increases when we go from top to bottom. The melting point is going to be different for the alkali metals and the halogens. So far, they've been exactly the same. Now, though, we have melting point increasing as we go from top to bottom for the halogens, but it is the opposite with the alkali metals. It increases as we go from bottom to top. Question 3.2.3 says diagram each of the trends listed for the standard 3.2.3, and that standard says to describe and explain the trends for atomic radii, ionic radii, first ionization energies, and electronegativities for the elements across period 3. So when it's saying period 3, that means energy level 3, which means we're talking about sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon. So we can talk about ionization energy first again. As we go from left to right, sodium to argon, we are increasing the ionization energy. It becomes more difficult or requires more energy to remove an electron from argon than it does from sodium. The electronegativity is the exact same trend as we go from sodium to argon. If we have, let's say, chlorine bonded to sodium, sodium chloride table salt, the chlorine is going to take that electron from sodium. It's not even going to bond covalently because it has such a much stronger pull, such a stronger electronegativity of that electron from the sodium. Then we look at the melting point. The melting point for this is going to increase as we go in the opposite direction. So from right to left, we're increasing. And that's the same for the radius. We increase as we go from right to left. So just the opposite of the ionization energy and the electronegativity trends. Question 3.2.4, it says order the following elements in increasing electronegativity. Luckily, all of those belong to the same group, or to the same period. They all have the same energy level. And so we think of those trends electronegativity again, increases as we go from left to right. So I look at my periodic table and I look at this period, period 3, which one's first of the ones that are listed? It's sodium. So that's my first one, followed by magnesium, followed by aluminum, then phosphorus, sulfur, and finally chlorine. Question 3.3.1, how do the chemical properties of alkali metals change as you go from lithium to francium? So lithium's up here, francium's down here. What's happening? We are increasing the reactivity as we go down. Those electrons aren't held as tightly because of electron shielding and because the radius is so much larger. So it's much easier to lose that electron, so it's more reactive.